Welcome to the Deep Dive. Imagine you're a teacher staring at a new class, or maybe you're building an educational tool, wondering if it's actually helping students learn.
Yeah.
How early do you know if someone is on the right track, or if they're quietly starting to struggle months before that big end-of-year test?
That's the challenge, isn't it? Those big, important assessments are few and far between.
Right.
It's like waiting until the final exam to see if the student understood anything all year. By then, for some kids, it's too late to really make a difference.
Yeah, the intervention window might have passed.
Exactly. And if you're developing software, waiting a whole school year to see if it moved the needle on state tests is, well, agonizingly slow feedback.
Absolutely. And that gets right to the heart of what we're diving into today. Can we get a reliable peek into a student's long-term potential much, much earlier? Specifically, this deep dive is all about a fascinating research paper that asked, how much can we actually predict about a student's end-of-year assessment results using only the data they generate in just the first few hours of using an educational technology program?
That's a pretty bold question. I mean, conventional wisdom might say you need a whole lot more data, or at least, a formal pretest.
Right. Hours seems like
Yeah.
not much at all.
It doesn't. The paper is titled Predicting Long-Term Student Outcomes from Short-Term EdTech Log Data, and it's the result of a collaboration between researchers at Stanford University, War Child Alliance, and Carnegie Learning.
That's an interesting mix.
It is. That mix of academic rigor and real-world application is pretty compelling right from the start.
It really is. So over this deep dive, we're going to explore the problem they set out to solve, unpack the different settings and data they used, because they looked across some very different contexts.
Yeah, that diversity is key.
Definitely. We'll see what specific behaviors in those early hours turned out to be the strongest signals, figure out just how short that short-term window can actually be, and talk about what this could mean for supporting learners.
That's it.
So let's start by digging a little deeper into why this early prediction matters so much.
Well, it's all about that slow feedback loop we mentioned. If you rely solely on infrequent, high-stakes tests, you just miss opportunities.
Right. Opportunities for what, specifically?
An early signal could allow for timely interventions within the software itself. Maybe the program adapts difficulty or offers different supports the moment it detects a student might be struggling based on those early behaviors.
So personalized learning, but based on predicting a future outcome, not just immediate success.
Exactly. Or it could offer richer challenges if a student is obviously excelling right from the start.
And it's not just about the software adjusting itself, is it?
No, not at all. This kind of information, if it's reliable, could be incredibly powerful for teachers. Imagine getting a report just a couple of weeks into the school year highlighting which students might need a little extra attention, or which ones might be ready for more advanced material.
All based on how they interacted with the learning tool early on.
Precisely. It shifts the support from being reactive, after a bad test grade, to being proactive.
That makes a lot of sense.
Now, using educational data to predict outcomes isn't completely brand new. People have certainly looked at predicting success using log data before.
Right. I remember seeing studies that used a student's entire year's worth of data from platforms like assessments to predict outcomes.
Correct. That's been a common and pretty successful approach. People like Ritter, Zhang, they've published on that.
Yeah.
And others have looked at prediction over very short periods, maybe just minutes or a single session.
But predicting what?
Usually that was to predict immediate success, like whether they'll get the next problem right or performance in that very first session.
Okay, so short-term prediction for short-term results.
Kind of. Think Gao et al. Or Mao's work focusing on the first problem or first minute. But predicting a test score months later from just that first hour or two, that's a much bigger leap.
It sounds like it.
Yeah.
So what made these researchers think it might even be possible, predicting long-term from such a tiny window?
Well, they drew inspiration from other fields, actually, like economics or clinical trials.
How so?
In those areas, they sometimes use what they call surrogate measures. Basically, a quick early measurement that's known to correlate strongly with a much later, harder-to-measure outcome.
Can you give an example?
Sure. Like predicting long-term employment stability based on someone's job status after just 1 year. Or, in medicine, using a short-term biological marker in a clinical trial to estimate long-term survival rates.
I see. The idea is that sometimes that early signal captures something really fundamental about the trajectory.
Exactly. The way someone starts might contain disproportionate information about where they're ultimately headed.
That's a great analogy.
And what makes this study particularly valuable, and a bit different, is that they tested this idea using just the first few hours of log data across multiple, very different educational contexts and tools.
Not just one platform.
Nope. And they focused on extracting features from the log data that are likely available generally, regardless of the specific EdTech platform. They tried to avoid relying on features unique to one system or requiring extra data like demographics or prior test scores, which, you might not always have.
Okay, so they had this bold hypothesis inspired by surrogate measures. How did they actually test it? What datasets did they use?
They used 3 distinct datasets, which really gives their findings more weight because they aren't just tied to one specific product or student group.
Okay, tell us about the variety.
First, there's the Can't Wait to Learn, CWTL reading dataset. This one's quite unique. It comes from students in Uganda.
Uganda, wow.
Yeah, using a literacy game program specifically designed for children in conflict-affected areas, grades 1 through 3. This dataset included 739 students, and the post-test they aimed to predict was an average score across multiple foundational literacy skill, letter knowledge, phonemic awareness, things like that.
That context alone is fascinating using EdTech in really challenging environments.
Absolutely. It's a world away from a standard U.S. classroom. Then the second data set comes from Mafia Math.
Okay, that one sounds more familiar.
It is. It's an intelligent tutoring system for middle school math, grades 6 to 8, used widely in the U.S. This had significantly more students, about 2,600.
Wow, quite a jump.
Yeah, 2,644 students. And here, they were predicting scores and achievement levels on a state end-of-year math test.
Got it. And the third?
That's iReady Math, another online math program for K-8, also in the U.S. For this study, they focused specifically on grade 7 students.
Just 7th graders?
Yeah, from a specific group of schools, 428 students in total. These were schools chosen because they tended to serve a higher proportion of students who were struggling academically.
Okay, so a more targeted group there.
Exactly. And the post-test here was the Smarter Balanced Assessment System, the SBAC.
So you have literacy in a conflict zone, general middle school math in the U.S., and 7th grade math in schools with higher needs. That's about as diverse as you could hope for, right?
It really is. It gives you confidence that any findings might not just be a fluke of one specific platform or, one type of student.
Makes sense.
So their basic approach was to see if they could build models using only the log data from those early interactions to predict those different external post-test scores months down the line.
How did they even measure that early interaction time? Was it just like how long the student was logged in?
That's a practical detail the paper actually addresses. Defining usage time consistently across different systems is a bit tricky.
I can imagine.
For the US-based systems, Mathia and iReady, they used wall clock time within active sessions. So if the student was logged in and interacting, that time counted.
Right.
But for the CWTL data from Uganda, they didn't have session data in quite the same way, so they used active time on each played minigame.
So just the time in the games themselves?
Pretty much. They do note this might underestimate the total time a CWTL student spent engaged, because it wouldn't necessarily count time watching instructional videos or just navigating menus, things like that.
Okay, a necessary difference based on the data available.
No.
So they have the data, they define the time window, but raw log data is just a stream of events, right?
Mm-hmm.
Clicks and timestamps. How do they turn that into something meaningful for prediction?
Right. This is where the feature engineering comes in. They didn't try to process the raw sequence of every single click or keystroke.
It sounds computationally heavy.
It would be. Instead, they focused on extracting specific features, basically, summary statistics and counts from the log data that capture student behavior. And the key constraint here was using features that are likely available in most educational software, not just one specific to Mathia or iReady. Generalizable features.
Got it. So what kind of behaviors did they quantify as these features?
They looked at several types. There were aggregate measures over the chosen time period, things like the total number of problems attempted, how many of those were successful.
Okay, basic counts.
Yeah, and importantly, the percentage of successful problems.
Percentage successful. That sounds like a pretty fundamental measure of how well a student is grasping the material early on.
It is. And spoiler alert, we'll see in a moment just how important it turned out to be.
Okay. What else?
They also looked at features normalized by problem or lesson. Things like the average number of attempts a student made per problem.
How many tries it took them.
Exactly. Or the average time they spent on a problem broken down by whether they ultimately succeeded or failed on it.
Time spent could mean different things, right? Fast could be good, or it could mean guessing. Slow could mean careful or stuck.
True. The interpretation isn't always simple, but it's a signal. They even quantified behaviors related to getting stuck, sometimes called unproductive persistence or wheel spinning.
Like what?
Like the number of consecutive failed attempts on a problem, or how quickly a student hit their first instance of this kind of unproductive struggle.
So not just what they did, but how they did it. How many tries, how much time were they flailing?
Exactly. They also included a few features capturing the most frequent sequential patterns of actions the students took, automatically extracted.
Okay. How many features in total are we talking about?
All told, they extracted somewhere between 16 and 26 different features from the log data for each student within that specific time window they were analyzing. Not a huge number, actually.
Manageable. And they also mentioned considering adding pretest scores later, right? Knowing that initial ability is often a strong predictor.
Yes, they did. They wanted to first see what the log data could do purely on its own,
Okay.
but also compare it to and combine it with pretest data, recognizing that pretests aren't always available, maybe for new students or if running them takes away instructional time, but they are a common predictor when you have them.
All right, the moment of truth then. They've got the data, the features, the different time windows, 1, 2, 3, 4, 5, 12 hours, and the full horizon data. How well did predicting long-term outcomes using just those first few hours actually work? This is the big question.
And this is where the findings get really quite striking.
Yeah.
What they found was that across all three diverse data sets, the machine learning models trained on log data from just a short horizon, meaning just a few hours of initial usage, were nearly as effective, and in some cases even more effective, than the best models using the full, much longer period of log data.
Wait, hang on. More effective from less data. That really challenges intuition.
It does, doesn't it? Look at the specifics. For the CWTL reading data in Uganda, the best predictive performance came from using just 5 hours of log data.
5 hours, okay.
Adding more data, going up to 12 hours, or using the full dataset available, actually slightly decreased the predictive performance of the model.
That's wild. Why would more data make it worse? Did they have a theory?
The authors speculate that maybe linking back to that surrogate index idea, after a certain point, adding more log data just introduces more noise, or perhaps it captures learning behaviors that are less fundamentally predictive of that distant end-of-year outcome, while that initial early signal is somehow cleaner or more indicative of the underlying trajectory.
Interesting. So the early struggle or success is maybe more telling?
Perhaps. It's not about predicting everything a student does all year, but capturing that initial direction they're heading in.
Okay, so 5 hours was the sweet spot for CWTL. What about the others?
For the Mathia data, the U.S. middle school math,
Yeah.
the best performance among the short horizons was with just 2 hours of data.
2 hours. Seriously.
2 hours. And that 2-hour model actually outperformed the model trained on the full horizon data for Mathia.
That's even more surprising.
It is pretty remarkable. For iReady, the 7th grade math group, the performance was actually pretty similar across the first few hours, from 1 to 5 hours, but 3 hours stood out as particularly strong within that early window, and it also performed comparably to using the full horizon data.
So we're talking predictions based on just 2, 3, or 5 hours of interaction, working about as well as, or sometimes better than, data gathered from potentially months of usage. That's a really powerful argument for the value of these early signals.
Absolutely. It suggests a lot of the predictive signal might be front-loaded.
Did the type of machine learning model matter much? They tested a few, right?
They did. They used linear regression, support vector regression, SVR, and random forest. The finding there was that the specific choice of algorithm didn't actually make a huge difference in the overall performance.
Oh, interesting. So it wasn't about finding some magic algorithm.
No, really. They all performed similarly well on average for each data set, and crucially, all of them performed much, much better than a simple baseline model, which would just guess the average student score for everyone.
Okay, so the signal is definitely in the data and the features they extracted, not just some fancy modeling technique.
Exactly. It validates the whole approach.
They did note, though, that the overall prediction accuracy, like the R-squared values, was lower for the CWTL data compared to Mathia and iReady. Any thoughts on why that might be?
Their hypothesis was it likely relates to data sparsity.
Meaning less data per student.
Yeah, students using the CWTL program, which was more game-based, might generate fewer logged events per hour or per minigame compared to systems like Mathia, which might capture more detailed steps within problem solving. Less dense data just makes prediction inherently harder.
Makes sense. Fewer data points to work with. Okay, so short-term data works off surprisingly well. Let's get into the features again. Which specific behaviors or metrics within those first few hours were the most important signals for predicting that long-term success?
Right, this is the next logical question. If we only have a few hours, what specifically should we pay attention to? They analyzed which features the random forest model, which often had a slight edge, relied on most heavily across the different data sets and time horizons. They were looking for a potentially stable set of predictors.
And did they find one? Was there much overlap between, say, predicting literacy in Uganda and math in the U.S.?
Yes, there was significant overlap. Two features consistently rose to the top and were often the most important predictors across the board.
Okay, what were they?
The first one was the percentage of successful problems completed by the student in that early window.
Ah, okay, we talked about that one seeming fundamental, getting problems right early on.
Exactly. It proved to be crucial. This feature was frequently in the top 5 most important features for prediction across all datasets and time horizons. And it was the single most important feature for CWTL writing at 5 hours and the full horizon, and also for Mathia at that optimal 2-hour horizon.
Wow. So just simple accuracy in the first few hours is a huge indicator. What was the other key feature?
The average number of attempts per problem.
How many tries it took them.
Right. This was also consistently high up, often in the top 5, and it was actually the number 1 most important feature for Mathia when using the full horizon data, and for iReady at its strong 3-hour horizon.
Interesting. So it's a combination of accuracy, what percentage you get right, and efficiency, how many attempts it takes you.
Precisely. How well and how efficiently a student navigates the initial material seems to capture a lot about their likely longer-term trajectory.
Were there other features that popped up as important across different data sets?
Yeah, there are others showing overlap, like the average time spent per successful problem was important for both Mathia and iReady. And the time until the first instance of unproductive persistence when they first got really stuck also showed up as important across both Mathia and iReady.
So if you're designing or using an EdTech tool, these findings suggest paying very close attention to these specific metrics. Early percentage success and attempts per problem, maybe time and getting stuck too, could give you a powerful, quite generalizable signal about student learning trajectories.
Absolutely. It points towards potentially universal indicators of learning progress in these environments.
Did they look at whether just one of these top features was enough? Like, could you just track percentage success and call it a day?
They did check that. And while using a single feature, especially percentage success, was definitely better than the baseline, just guessing the average.
Right.
Using the entire set of 1626 features they extracted consistently led to better predictions than relying on just one or two.
So the combination of signals provides more nuance.
It seems so. The whole picture painted by all those features together is stronger than just one brushstroke, even if that one stroke is very important.
Okay, this is great for understanding the overall prediction power, but what about using this information for individual students? We touched on teacher dashboards. How well did these models actually predict for students at different performance levels? You know, the ones who might really struggle versus those likely to ace the final test.
Yeah, this is where the practical application gets maybe more nuanced and more critical to understand. They looked at this by dividing students into 5 performance groups, quintiles, based on their final test scores.
Okay, lowest 20%, next 20%, and so on up to the top 20%.
Exactly. And also, just for Mathia, they looked at a simpler binary split, on track versus not on track, based on the state test's passing score categories.
Makes sense. So what did they find about predicting for these specific groups? Could the models accurately place students in their eventual quintile?
Overall, the models were not highly accurate at predicting the exact performance quintile for every single student. They especially had a harder time distinguishing between students in the middle groups, like Q2, Q3, Q4.
Okay, so they couldn't perfectly pinpoint if a middle-performing student would end up being exactly in the 3rd or 4th quintile based only on those first few hours.
Right. There was more confusion in the middle. But, and this is the key practical takeaway here, the models had much higher precision at the extremes.
At the extremes, meaning the lowest and highest groups.
Exactly. Q1, the lowest performing group, and Q5, the highest performing group. What high precision means is that when the model predicted a student was likely to end up in Q1 or Q5, that prediction was often correct.
Ah, so it might not be perfect for classifying everyone in the middle, but it seems pretty good at flagging potential high flyers or those most at risk based only on that early data.
Precisely that. For example, for CWTL Reading, the random forest model had 77% precision when predicting a student would end up in the lowest quintile, Q1, and 72% precision for predicting the highest, Q5.
77% is pretty high for identifying the most struggling group early on.
It is. For iReady, the precision was 57% for predicting Q1, a bit lower there, but a very impressive 88% for predicting Q5, the top performers.
Wow, 88% for the top group.
And for Mathia, using the SVR model, it was 70% precision for predicting Q1 and 61% precision for Q5.
Those are significant numbers if you're a teacher or a system designer trying to identify students who might need targeted support or maybe enrichment very early in the school year.
Yes, and looking quickly at that Mathia on-track, not on-track prediction.
Yeah, the binary one.
The model correctly identified many students in both groups, classifying over 1,500 as on track and over 400 as not on track correctly. However, it did have lower recall for the not on track group, about 0.44 recall.
Okay, what does low recall mean here?
It means it missed a fair number of students who actually ended up not being on track by the end of the year. It failed to flag them based on the early data.
So it didn't catch every student who would eventually struggle?
No, definitely not every single one. But similar to the quintile finding, when it did flag a student as likely being not on track, that prediction had reasonable precision, about 74% accuracy.
Okay, so the alerts it does generate for potentially at-risk students are reasonably reliable, even if it doesn't catch everyone.
That seems to be the pattern. The alerts for the extremes, both high and low, tend to be fairly trustworthy, more so than trying to pinpoint exact middle performance.
This is really relevant for you listening. While these early data models aren't perfect crystal balls for every single student, their ability to often reliably identify students likely to be at the very bottom or very top based on just a few hours could be incredibly useful for prioritizing resources or thinking about differentiated instruction right from day one.
Absolutely. But the paper does add, and it's a crucial point, a strong note of caution here.
Which is?
Any potential tools or dashboards based on these findings would need really rigorous testing and validation in actual classrooms before they were used for real interventions.
Why the strong caution?
Just to make sure they are truly effective and, importantly, don't have unintended negative consequences. Like mislabeling a student early on or causing undue anxiety. You have to be careful with predictions.
That makes complete sense. Responsible implementation is key. Now, earlier we talked about how this study focused mainly on log data, in part because other things like pretests aren't always available. But what if a pre-assessment is available? How does that change the picture? Does it make the log data prediction less important?
That was their final research question, RQ5. They directly compared using only the log data features, using only pretest data, and then combining the two.
Okay, and the result? How do pretests stack up?
Unsurprisingly, pretest scores alone are a very strong predictor of long-term outcomes. That prior knowledge baseline is powerful.
Right.
Models using only pretest data generally perform similarly and sometimes even a little bit better than models using only the short horizon log data features. The RMSEs, the error rates were quite comparable.
So if you've got a good pretest, that gives you a solid head start on prediction right there.
It absolutely does. But the good news is it doesn't seem to be an either-or situation.
Oh.
They found that combining pretest scores with the short horizon log data features often provided additive gains.
Additive gains, meaning better than either one alone.
Generally, yes. It often led to slightly better overall prediction performance. Particularly, it improved things like the R-squared value, which is a measure of how much of the variation in the final scores the model could account for. Combining them explained more.
So using both signals together, the pretest and the early log data, is often better than using just one.
It seems so. For example, combining pretest with short horizon log data using the SVR model pushed the R-squared up to 0.44 for CWTL Reading and an impressive 0.66 for iReady.
That's explaining a lot more of the outcome.
It is. And combining them also seemed to help refine the predictions specifically for those students at the extremes, the Q1 and Q5 groups, leading to less over or underestimation compared to using just the log data alone.
That makes intuitive sense, doesn't it? The pretest gives you a baseline snapshot of prior knowledge, and the early log data gives you a dynamic snapshot of how they're engaging right now with the new material or platform. Using both gives you a more complete picture.
Exactly. It's like having two different valuable viewpoints. The takeaway here seems pretty clear. If you have pretest data, absolutely use it. It's powerful. Combining it with early log data is likely your best bet for the most accurate prediction.
Okay.
But, and this is important, if pre-tests aren't available maybe for new students transferring in, or if the school decides against using testing time for pre-assessments, this study shows that the short horizon log data alone still offers significant predictive power.
It's still valuable on its own.
Very much so.
Yeah.
And in that case, using that comprehensive set of features extracted from those logs is better than just looking at one simple metric like percentage correct. The full feature set matters.
This has been a really eye-opening dive. Let's try to quickly recap the big picture here.
Okay.
This research makes a pretty compelling case that we might need far less data than previously thought to get a valuable early signal about a student's likely long-term academic performance.
Yeah, that's the headline finding. Just a few hours of interaction with educational software, sometimes as little as 2 or 3 hours.
Right, like with Matthew.
Can provide predictive power that's comparable to, or sometimes even better than, using data collected over months.
And importantly, they've identified that certain, maybe fundamental metrics captured in those early hours, like the percentage of problems solved correctly and the efficiency, the number of attempts per problem,
Those two stood out.
seem to be consistently important signals across different types of learning tools and really diverse student groups.
That generalizability across contexts is a key strength.
And while these early models aren't perfect at predicting the precise outcome for every single student, especially those in the middle,
Right, the precision wasn't as high there.
they show real promise in reliably identifying students at the extreme ends of the spectrum, those who might be heading for significant challenges or those who seem set to really thrive based on just that initial engagement.
That high precision at the extremes, Q1 and Q5, is probably the most actionable part for early support or enrichment.
Which brings us to something important for you, the listener, to consider. Given this potential for early signals from educational technology to help us understand student trajectories much sooner, what are the practical challenges and the really important ethical considerations we would need to address to effectively and reliably integrate these kinds of predictions into real-world teaching and learning environments?
That's the million-dollar question, isn't it? How do we ensure the predictions are accurate enough? How are they communicated sensitively and usefully to educators or maybe even students themselves?
And crucially, how can we make absolutely sure this information is used primarily to empower and support all learners and not inadvertently create new labels or pressures? What safeguards do we need?
Lots to think about there before jumping straight to implementation. The validation step they mentioned is critical.
Definitely. Well, that's it for this deep dive. We hope this exploration of using short-term data to predict long-term outcomes has given you some valuable insights into the potential and perhaps the complexities of using educational technology to gain an early understanding of student success.